So, if you watch the power generation video and where does my electricity come from, you remember that basically electricity comes from turning turbines. At least that's where most of it comes from. And you can physically turn turbines like this, or you can use air bending like this. But in real life, you can use water bending, wind turbines, or you can use steam and pressure to do it, where you heat up water and that water turns a turbine with pressure, and the pressure allows the turbine to turn. But whatever the case, we need to figure out how we can actually calculate the input power from that turbine. How do we know how much power we're actually going to get with that turbine? And that's what this video is about. So, I'm going to derive the equation for you on the power of a turbine. One way to make the turbine turn without actually physically turning it is to use wind turbines, all right? Where you actually use wind power and actually turn a turbine that way. Now, here's an example. I'm going to turn on my wind here, this fan, and we're going to see how it actually can physically turn the turbine. So, whether you use wind or water or steam to make the turbine turn, it always results in the same process. You're turning the turbine, which turns the generator, which produces alternating current. And that power generation video I made kind of goes through that whole process. Let's just kind of derive the equation for the power in a turbine. So let's kind of break it down into pieces. Let's remember that power is just energy over time. That's the equation for power. Now, that's kind of helpful for us, but we need to know more specifics with, let's do an example with like the wind turbine. All right, doesn't have to be wind, but we need more information. So let's say we had wind blowing into this turbine, and it makes it spin. Well, the energy of the wind is kinetic energy. It's moving. That moving energy is going to do work on the turbine. So the power is going to equal kinetic energy, which is 1/2 mv squared divided by time. Now I'm going to write the time underneath the mass. It's underneath the whole thing, but it doesn't matter if you divide any one of these variables by time, it's still the same mathematically. Now, if you remember, mass divided by time is flow rate. It's the mass flow rate. So if I know the mass flow rate of the wind, and I know the speed of the wind, I can figure out the power. Okay, well, let's say I don't know the mass flow rate of the wind. What else do I possibly know about the wind? Well, let's look at the equation for density. This is the symbol for density. Density is mass divided by volume, big V. So if I solve for mass, mass is equal to density times volume. So let's rewrite the equation. Power equals 1/2 times density times volume. And then I'll divide the volume by time times velocity squared. The velocity is lowercase v. All right, so that's another equation for power. 1/2 times the density of air. I know that. It's usually about 1. Or water, it's about 1,000 kilograms per cubic meter. So I can know that. That's something I know. Times the volume flow rate, which is a volume per second, times the speed squared, or velocity, because it's directional. Okay, well, it's kind of hard to find the volume flow rate as well. Possibly it's possible, but let's kind of break it down into pieces. How do I find the volume of air, the volume of water, volume of steam, whatever it is that I'm using? Well, volume is just the area of the blades. It's the area of the blades times the amount of depth or amount of space being given into the blades at a certain amount of time. So it'd be like this much distance. So this distance times the area is the volume. That'd be like the whole volume. You can imagine a cylinder of air or a cylinder of water going through that turbine. So I'm going to replace that volume with area times distance. So power equals 1/2 times the density times the area of the blades times the distance over time, because that time factor is still there, times the speed squared. Oh wait, what's distance over time? Distance over time is velocity. So if I know the distance over time, I can just replace it with velocity. And velocity times velocity squared is just velocity cubed. So this is probably the most useful equation to use. I'll actually write one more step here so we can use that. But the power in the turbine is going to be 1/2 times the density of the fluid, whether it's steam, air, or water, which we can look up or just know, times the area of the turbine. You can usually approximate that with a circle because it's spinning and it makes a circle. So if I want to go one step further, I can replace the area with pi r squared, where r would be the length of a turbine blade. That would be the r. The length of a blade would be the r, times the speed of the wind, water, or steam cubed. Nice. Now, there's going to be an efficiency factor as well. No turbine is 100% efficient. First of all, there's some gaps in the area here. So that's going to tie into the efficiency. But if we approximate this as a circle, we can worry about the efficiency later because the power is going to be this times some efficiency. All right? And there's going to be some dissipated energy along the way too. But like I said, that can be all tied into the efficiency factor. Remember, efficiency is just output over input or useful over total. Well, we can worry about that part later. But if we want the input power, that's what we can get, is that input power. 1/2 times the density of the fluid, times the area of the turbines, which is pi r squared, times the speed of the fluid cubed. Nice.